It's a pleasure to be here at Harvard and to tell you about future missions. It's even more of a pleasure lately as my daughter is a graduate student in applied physics, so I had dinner with her last night and we rubbed the toe of John Harvard. So we're living in a very exciting and exceptional time, I think, right now with these 4 big observatories observing in the hard X-ray and gamma ray band. And we hope that this continues for a long time into the future. And at the end of my talk, I'll sort of talk about how long this probably will continue. We don't know, but we can make a guess. But I want to look in this talk today, what's going to happen beyond these missions and how we'll be able to address the science and supernovae, tidal disruption events, gamma ray bursts, gravitational wave events, all the things that we're looking at in this transient sky workshop. So this is a beautiful example of the power of these current observatories. This is a multi-wavelength campaign on the Blazar Markarian 421. It's a very active Blazar. A lot of variability, so you need to observe simultaneously across the whole electromagnetic spectrum to really see how the SED evolves. And when I first started in astrophysics, actually in graduate school, and just after that I was working on these multi-wavelength campaigns, and it was really hard to get all these separate observatories. It's still not easy. But Fermi's covering the whole sky all the time. Swift has 3 instruments on board covering UV, X-ray, gamma ray that can be easily scheduled. And we have, a large number of radio facilities now available. And so it's becoming much easier to do these kind of campaigns because we have so much coverage. Not to mention, going up into the high energy band with the ground gamma ray instruments. So, it will be hard in the future to have such good coverage over the full electromagnetic spectrum, but that's the goal. So I wanted to give you a little tutorial since I'll be talking about instrumentation, just a few slides. There's various different kinds of ways of imaging and collecting light. You can do multi-layer, you can do grazing incidence mirrors in the X-ray band, and if you put multi-layers on them, they work up into the hard X-ray band. That's how NuSTAR works. And there's many sort of future, more capable missions than NuSTAR that are being considered for the future in the next coming decadal survey here in the US. Coded apertures are a really nice way of imaging a large part of the sky at the same time. That's how the BAT instrument on Swift works. I'll show you that in a minute. Compton telescopes are good for going up into the MEV band, where the Compton process is the one that dominates as light interacts with matter. And pair production telescopes are the way to go into high energy band. So with Swift and let me first show you detectors and then I'll get to Swift. So the detector types, more or less in the old days, but we still use these quite a lot, like the GBM instrument on Fermi as an example. Used scintillators and photomultiplier tubes. Solid state detectors are much more common nowadays and much easier to use, but sometimes still photomultipliers are good. And for pair trackers, usually there's lead material that produces the electron-positron pair, and then this can be different kinds of materials. Here, I'll show you some of these different names here. Egret had a spark chamber to read out the positions for the tracking the pairs. But Fermi has silicon detectors, 68 square meters of silicon in their instrument. It's a huge amount. And you can see these different materials used here. So here's my Swift example. This is for coded aperture imaging. And so for the BAT, we have this aperture at the top, which is lead tiles, little lead pieces glued onto a board. And below that are a lot of cadmium zinc telluride detectors. Actually, there are 32,000 of them. So this is the most capable coded aperture instrument that's been flown. And it's because of that we're so sensitive to gamma ray bursts. And you can see it. The advantage of this coded aperture technique is you cover a lot of the sky, and it's the way to do gamma ray burst and transient object detection. The disadvantage is that to make any image of any source on the sky, you need to add up the signal from all the detectors in your detector plane. So there's a lot of noise that you're adding in. These kind of instruments are much less sensitive than focusing instruments. But, and I'll show you an example that we want for the future, which is an X-ray focusing telescope that has a wide field of view to get the advantage of both techniques. But currently, if you're going to focus X-rays, it's with a narrow field of view instrument. And so now looking at the science requirements, for future instruments, we just heard about gravitational wave events. You want multi-wavelength coverage, rapid response. That can be quite important. If we look at the afterglows that we get from short gamma ray bursts and they decay off very quickly, want to be able to observe within the first hour or few hours, and a wide field of view. Especially right now, the position accuracy is very poor, as Brian showed. But it will improve as other gravitational wave interferometers come online. And it's exactly the same requirements for all areas of time domain astronomy. For supernovae, you need wide sky coverage to detect the supernova in the optical. And then if you want to do follow-up with other instruments in the radio or with Swift UVOT, you want a rapid response and good time coverage, be able to keep observing the supernova through the whole light curve. You can see we go through all these different requirements, so I'm not going to go through each one now. Polarimetry is something that's become very, on people's mind because we really haven't had good polarimetry missions. And it's a good way to look at magnetic outflows and really diagnose jets in different sources. And so there's a number of concepts being looked at for capable hard X-ray through gamma ray polarimeters. This is a plot of the instruments that have flown in the gamma ray band. This is sort of hard X-ray gamma rays, includes some sort of regular X-rays too, but it doesn't cover all of the X-ray instruments. And you can see that there are a lot of missions that are flying right now and will continue. This is a little box that's sort of some of the techniques that I'll be talking about, missions and mission areas like MEV, GEV concepts, some of which are already in development, but most of which are concepts that people are thinking about. So I'm first going to talk about missions that are flying, have recently been launched and are flying, and then SVAM, which is in development right now, is sort of a follow-on to SWIFT. So I'll go through those, and then after that we'll look at some of the concepts that people have for the time beyond that. So you may have heard about Icarus or GAP. It flew for just a couple of years. It's a very tiny instrument. It's only 4 kilograms, and it's a Compton scattering instrument. But for gamma ray bursts, that 4 kilograms was enough to look to see if there was polarization in the prompt phase of the gamma ray burst. And so they caught a few bursts, and one of them had a good enough signal to give this polarization measurement. It's only a 3.5 sigma detection of polarization. You can see the contour plot here. It's not very significant. It's hard to tell exactly, but it looks like there's a hint here that there's polarization at about the 20% level in the prompt phase from a gamma ray burst. And there have been indications from other missions, RESC and Integral, of high polarization percentages in prompt phase, but we really want to pin this down. It's very much in its infancy. That was a Japanese instrument. Here's an Indian instrument, AstroSat. It's just been launched. It's got 5 instruments on it. It's a very capable satellite. It's not a Swift-like rapid response telescope. It's more like a RXTE with large area detectors for looking at pulsars and many other sources in the sky. Large area proportional counter. It has a CAD-Zinc tail-coated aperture instrument, but not a very huge field of view. So, it detects some gamma ray bursts, but not a lot. A all-sky monitor like the ASM on XTE, and an X-ray telescope and a UV telescope. They've just been turning on their first light images with Swift. We've been working with them to calibrate their instruments. And so, I think it's very capable. So I'll talk about SVAM next and use Swift as an example of what has been happening recently in the mission and what SVAM has been doing to sort of adjust their satellite. So we started out observing with gamma ray bursts. Most of our observing time was Swift. We launched in 2004. But as time went on, there were more and more requests for target of opportunity requests for people to use Swift data looking at other kinds of objects. Transient objects mostly, but all kinds of objects and monitoring campaigns. And this has gotten to the point that there are now 4 per day of these that are coming in. And many of you in the audience are the ones that are putting these in, so you know all about it. For gamma ray bursts and supernovae and novae and tidal disruption events and blazar flares and everything all, under the sun. And you can see how the SWIFT findings have been a really nice mixture of GRB results and things that we detected on board with the BAD instrument and followed up, or things that people called in about on our TOO webpage and we pointed out. And so the SWAM mission, which was a Chinese-French mission for years, if you've been following this saga, there were political turmoil and the mission wasn't moving forward. But now finally the Prime Minister, President and Prime Ministers of China and France have signed the document. And I actually went to a meeting 2 weeks ago, so I can give you the latest news on SWAM. It's in development, and it is going to launch. Right now, their launch prediction is 2021. And this will really be a follow-up to SWIFT. It has a coded aperture instrument that goes from 4 to 250 keV, so a little bit more into the soft band than SWIFT does. SWIFT only goes down to 10 or 12 keV. A GRM instrument, which is, sort of like GBM. I'll show you a little bit more. So this meeting was Les Ouches. If you've been there, it's a beautiful place to spend a week. And, I was there with the SWAM team talking about all their details. So here's what their payload looks like. This Eclair instrument is being developed in France. It's a very capable coded aperture instrument. It'll detect about 70 gamma ray bursts per year, so it's very similar to what SWIFT does. And then the X-ray instrument is predominantly being developed in France, but it's actually uses a microchannel plate optic. It's a new technology optic to have a very light X-ray telescope. This is a visible telescope. These are the scintillators for the GBM-like instrument called GRM. And they also are building several ground telescopes that'll be part of their network. 2 narrow field ones, one in France and one in China. And this GWOC is a wide field of view optical telescope that'll be pretty capable. Sort of some of you are working on these instruments or have them operating right now, sort of like Raptor is one example, and it's in Tibet. SWAM is going to be an anti-solar pointing telescope. SWIFT points all over the sky all the time, and a lot of times we're not pointing in the anti-sun direction. And this has been an issue for GRBs because you don't want to detect a GRB near the sun, but we detect some of those with SWIFT. And so SWAM has purposely decided to point all the time in the anti-sun direction. It also was the way that they could afford the spacecraft it's a fairly lean budget mission. And so they'll get 70 GRBs per year, but they'll all be in a good position on the sky for ground-based follow-up, nice dark part of the sky. A disadvantage of this is that half the time they're going to be pointing, their instruments will be pointing at the Earth, so that they lose 50% efficiency, but they still get a really good number of gamma ray bursts. And one thing that's new with SWAM is that they have added a TOO capability, seeing that there's lots of other kinds of transient science. And it's not bad. It's sort of 1 TOO per day is what they're going to start with. So I think that's a really nice development. Okay, so now we'll look towards the future. And I'm not going to go through all of these, but I'm just going to highlight a few of them. There's a lot of different concepts that are being looked at right now. This XIPE is actually a phase A study from the M4 round in ESA. This one, there are 4 missions, and one of them will be selected. So it's not in development, but it has some, it's been chosen from many candidates. And these are other missions. This is an XTE-like mission. This is a transient observatory. This is a high-energy MEV, GeV. They're going to go into the next round. And here are some concepts that people are working on, and maybe I've missed some that I don't know about or I've forgotten. That'll go into the next Explorer round, which will be a mid-X, and the proposals are due in the fall. I'll talk about some of these. And then there are bigger missions that the US and the international partners are looking at, or international agencies are looking at. And so For the decadal survey, there's a probe class, which are missions just under $1 billion, or there's even larger ones. And NASA headquarters is going to release a call probably next year that will give funding for people to look at different probes. And so there are many different ideas. TSO is one that Josh Grindlay is doing here at Harvard. And then on the exact opposite side are CubeSats. There's a huge outflow of interest in CubeSats. And here are some that are, this is a gamma ray burst one. This is a wide field gamma ray burst and other kinds of science. This is for TGFs, and this is a UV mission. Internationally, there are some pretty big missions that are in develop, or I guess they're actually in development. Maybe I should have called them in development earlier. But their launch date keeps slipping, so I'm not exactly sure when they're going to fly. Russian instrument for gamma ray bursts, and it's a very small instrument. This is a Chinese instrument, sort of like XTE. Wide field MAXI, it's an enhancement of the MAXI payload that's on the space station. And Gamma 400 is a Fermi follow-on that the Russians are looking at. These are sort of context missions or instruments. I'm not going to talk about those, and the ground-based ones. So these are the ones I'll say a few more words about. So I'm going to concentrate on the Lobster, sort of transient observatory, and on the high-energy missions, MEV gamma ray, following up on the Fermi LAD instrument. So Lobster is a mission that we've been looking at at Goddard, but with a number of partners in the U.S. and internationally. And so this is what we call Lobster. The Chinese have something very similar called the Einstein probe. And we've been to meetings over in China, and this is a very capable, very similar instrument to Lobster. I'll describe these in a minute. And then there's a version of Lobster that Jordan Camp, who's here at the meeting, has been looking at to fly on the ISS. This is what we'll probably be putting in with Jordan as the PI to the next NASA call, the MIDEX call. It's called ETA. So what it does is it gives you a wide field focusing capability. This is the thing that we've always wanted, and there is a new technology that allows this. And it takes advantage of the exact design that lobsters and crustaceans have in their eye, which is sort of these egg crate structures where the photons come in and scatter off the walls, so they're focused, but you can make a curved surface, just like a lobster's eye looks like. And so you can see over a wide field of view while you're still doing focusing. It's also nice because it's a really light technology. To make a much more capable BAT instrument would take thousands of kilograms and be so expensive. And this is something that can be afforded on a MIDEX or SMEX budget. The sensitivity is much improved. It's over a magnitude more better, for transient sources and for gamma ray bursts. And this is for this version of it that's shown here. So it's it'll be a huge step forward. This is an X-ray instrument, so we'll be looking for gamma ray bursts and other transients and gravitational wave follow-ups in the X-ray band. These are the parameters. It covers 0.5 steradians. So that's great for gravitational wave follow-up. We can cover the whole error box, even for the current gravitational wave events. That's one of the things we're really focusing on in this current round. Here's the energy range from 0.3 to 6 keV. And one of the, on SWIFT we have a UV optical telescope. We've always thought it would be nice to have an infrared telescope because certainly GRB afterglows, the more interesting ones are in the infrared band. And so we have an infrared telescope in this concept that we'll put in as a MIDEX with a 40 centimeter mirror diameter going out to 2 microns. And then, it'd always be the really beautiful, most ambitious instrument that we can think of that would fit within $1 billion. We're going to put in, or some other, there'll be people around the country and that'll be doing this for the U.S. probes in the next decadal survey, and in Europe and maybe other places in China, looking at really capable ones. So this one has 9 Lobster modules, 2 steradian sky coverage. It's an incredibly powerful mission with an infrared telescope and an X-ray telescope. And it's something we're looking at for the more distant future. This is the kind of sources, and I think when we made this, we didn't have gravitational waves in mind, but now gravitational waves have been sort of one of the most important drivers. But there's also tidal disruption events, all kinds of shock breakouts that we've been hearing about at the meeting, SGRs, novae, and regular gamma ray bursts. Since this instrument operates in the soft band, it's really good for high redshift gamma ray bursts. There'll be, this mid-X version gets, several per year at Z greater than 5. It's not so good for short gamma ray bursts, so we'll have some scintillator instruments on board also. So now I'm going to switch gears to the high energy band. What's going to follow on the Fermi instrument or Agile that is operating in Europe? So these are the technologies that are of interest. Silicon strip detectors, perhaps two-sided ones. The LAT instrument has one-sided ones. Scintillating fibers is a much cheaper technology that we might be able to build a much bigger instrument. And one of the things that we want to focus on is looking in the softer band going down in the MeV range. But this is sort of where the space opportunity is to match up with the sensitivity with the CTA instrument, which is being built internationally, being led in Europe, which is a very powerful ground instrument in all the areas of science. And we're still sort of pretty far away in angular resolution from what you could do with the kinetic limited instrument. And so this is sort of where Fermi is. And so I think there's an opportunity to have a better imaging capability. So these are the different concepts that I know of. And I should put Gamma 400 on there, which is the Russian instrument, which is similar. But so compare is one concept, which is very much like the LAT instrument, but it takes out the lead converters, so it gets down into the MeV range. Adept is a large gas detector. And Astrogam is similar to compare. It's a silicon strip tracker without converters. So last thing I wanted to mention is sort of what's the future for Swift and Fermi? How long are they going to last? Because everybody always ponders that question. So in the past, we've done well in this senior review. So I'm looking first at funding. Every 2 years, there's a review that NASA does of all its operating missions, and Fermi and Swift have done quite well in those. We're actually waiting any day now to hear the results of our presentation this year. And so that'll determine the funding for the next 2 years. But I don't think either of these very capable missions are going to be turned off for lack of funding, at least looking ahead for the next 5 years. So then the next question is, well, maybe they'll be limited by orbital lifetime. And both of them have, lifetimes that are going to last probably well into the 2030s. If the sun got very active, which is not doing it all, we could come down as early as the early 2020s, but it's still quite a ways from now. And so then the last thing, which is probably what we'll do both of them in, is the parts lifetime. And there's this sort of famous parts failure curve called the bathtub curve, which is just after you launch a satellite, parts get exposed to radiation and there's infant mortality and they break. But then you enter this nice long period of time. XTE was sort of at this phase for about 12 years when everything is stable. And eventually the radiation dosage just builds up and eventually parts start failing again. And I don't know when that happens. It's just from my experience in this business for more than 20 years, something like 15 years after launch, but who knows. And Swift was launched in 2014, Fermi in 2008, 2004 and 2008. So you have a feel that if things go well, we might still get a few more years out of them. So I think we're living in a very privileged time with this observatories, so many observatories all working, and it looks like that may continue for at least several more years. The future missions are going to be smaller and more focused and may not have the full coverage of the electromagnetic spectrum, but we hope they do. I'm really impressed with SWAM. I thought for years that it wasn't ever going to fly, but it looks like it will, and it's capable. Well into the 2020s, it'll be giving us gamma ray burst triggers and be able to follow up on supernova events. It's a multi-wavelength payload. CubeSats are something to keep an eye on. All around the country, people interested in these. And how can you, for just a few kilograms, how can you do something capable? Well, you can have a lot of them. You can actually cover the whole sky. This is one of the things that Josh wants to do. 4 pi steradian, and do gamma ray bursts. There's a concept like that at Goddard, too. And India and China, there are other countries like Japan and Russia that have been in the space business for quite a while, but India and China are now getting into space science with very capable instruments. And I talked a little bit about these new technologies that I think will give a great promise for gravitational wave follow-up and gamma ray bursts in the MeV range. So, thank you.
Neil, in regards to Svalman, you talked about this in the context of Lobster. Do you have any idea why they're still going for an optical telescope instead of an infrared onboard capability, and could that change?
I don't think it's going to change, but it will go into the red band further than the UVOT does. But it's harder to do an infrared telescope. The Chinese are doing the visible telescope, and they don't have I guess they could probably buy the H2RG detectors, but it's more expensive, and they just have not been able to afford it or afford the risk of it. It would be nice. So we're going to depend on ground follow-up again.
So Hitomi died. How does that affect the plans for future of X-rays? The microcalorimeters from Goddard, is NASA going to make a priority to put that up there on some satellite?
So it's very sad. All those people are working down the hall from me. JAXA is right now considering how to, whether to refly Hitomi or not. And so they're having discussions with NASA also. And it could well be that they will decide to redo Hitomi. And I'm speculating now, and I'm not speaking for NASA, but I would guess if that happens that NASA will decide to provide the calorimeter again. It may have to go into the next mid-X round as a MOO proposal, or maybe it'll just be put in since it was, a loss of hardware. If you look at the past when there have been missions that have been lost, NASA tends to just rebuild them, without competing them again. So we'll have to see how that develops. If that doesn't happen, I would guess that that there would be a full mid-X proposal for a mission that would have a calorimeter on it in the U.S. I don't know if you saw the Nature paper with the beautiful results on that instrument was working perfectly when the spacecraft died.